Distributed forces. Now watch this diagram. Here it's a wooden plank on two simple supports and a man is standing on the wooden plank. Let mass of this man be 100 kilograms multiplied by 9.8 meters per second squared and you get weight of the man as 980 Newton. So force exerted by this man on this wooden plank is 980 Newton. It is the same wooden plank and he is the same man standing on the wooden plank. But now he is standing on its single leg. Now same man is sitting on the wooden plank or he is sleeping on the wooden plank. In all these four cases, is it not the same force exerted by the man on the wooden plank? Yes. How we show force exerted by the man on the wooden plank? So this is how we show it. We show that this is the force exerted by the man on the wooden plank at this point. Is it really acting at a single point? No. The force exerted by the man is distributed on certain area. His feet are in contact with the wooden plank and at the area of contact his weight is distributed. Now here the weight of the man is concentrated more now in the smaller area. Same man is sitting on the wooden plank, so area of contact is more and here area of contact is much more. What you should understand from this example that a force can be distributed in infinite number of ways. And when a distributed force is on a rigid body, it can be replaced by a point force. This force is nothing but the resultant force. So force acting at a point is a theoretical concept. In practice, many times we can approximate a distributed force as uniformly distributed force or uniformly varying force. So what is that? Let's try to understand. A uniformly distributed force. First of all, how it is shown in space diagram. So this is how it is shown in the space diagram. It is always associated with its length. What does this diagram suggest you? Each 1 meter is carrying 200 Newton for 5 meter length. So uniform distribution it is. 200 Newton per meter weight per unit length, that is known as intensity of the distribution. So if 200 Newton per meter load is acting over length 5 meters, then it's simple mathematics. What is total force? 200 into 5, that is 1000 Newton. So this is how we show it in the space diagram. So it is a 5 meter long rod and at the center of the rod, the 1000 Newton force is acting. That is, when it is uniformly distributed load, it is to be shown at the center of its length. And direction is obvious here, it is downwards. And magnitude as if you are finding area of rectangle. Base 5 meter into height. Height is nothing but the intensity of loading. So base into height and you get area of rectangle formula. Now there is one more conventional method to show a distributed force in a space diagram. Now this diagram suggests you the same thing. The distribution is uniform. It is 200 Newton per meter over length 5 meters. So it is to be shown in the space diagram in this manner. At the center of its length, 200 into 5, 1000 Newton force. So this is how a uniformly distributed force is shown in the space diagram. But if this distributed force is acting on a rigid body, then it can be shown as a point force in this manner. But how will you come to know direction of this load? I've shown here it downwards, but why it is downwards? Try to understand. Now listen, this is one standard method to show a uniformly distributed force or uniformly distributed load. As a point force, I have shown here it as a downward force. But how will you come to know direction of this force? Listen to me very carefully. This notation is used above the length AB. So from above it is push type of force. So to make you understand it better, watch here this example. Here the notation is used below line AB. So from below it is to be shown as a push type of force, and of course at the center of its length. So now you will able to tell me easily. Check here, on a vertical rod a distributed force is acting, a uniformly distributed force is acting. So on which side that notation is used? From that side, push type of force. One more example here. On which side of line AB this distributed force is shown? From that side it is push type of force. And similarly in this example, check here. Now line AB makes 30 degrees with horizontal, so its normal makes 30 degrees with vertical. Hope you have understood how to replace a uniformly distributed force by a point force. Now, sometimes a distributed force is approximated as a uniformly varying force in this manner. So its outlined shape appears as a triangle. What this triangle suggests you? Listen, base of this triangle is nothing but length of the UVL. UVL means uniformly varying load. So 6 meters is the length of the UVL in this diagram. So UVL is associated with its length, and in distributed load diagram, height of that load diagram is intensity. So maximum intensity is at point B, and that is 200 Newton per meter. Intensity at end A is 0, and this intensity, that is nothing but height of the load diagram, this intensity is increasing uniformly from 0 to maximum. That is what you should understand from this diagram. But if such a load is acting on a rigid body, how to show it as a point force? Use the logic of a triangular area and its centroid. Where centroid of a triangular area lies 1/3 of its length from its edges. So from maximum intensity end, from maximum intensity end means from end B. So 1/3 of its length from maximum intensity end. That means the distance from end A is 4 meters. So 1/3 of its length from maximum intensity end. And show the load 600 Newton. How come 600 Newton? Basic logic is average intensity into its length. So 200 at this end, 0 at the other end. So average is 200 by 2, that is 100 Newton per meter. So 100 into 6, that is 600 Newton. But better way to remember it as area of a triangle. Base into height. Height is nothing but the maximum intensity of the uniformly varying load. Base into height by 2. So 6 into 200 by 2. Area of triangle formula. This is how we find total force by a uniformly varying load. Base into height by 2. Here it is a distributed force. It is a uniformly varying force. But variation in intensity is 10 Newton per meter at end A to 25 Newton per meter at its end B. How to show this force as point force? Try to understand. We consider this distributed force as a combination of a rectangular force and a triangular force. Intensity at one end is 10 Newton per meter and the other end is 25 Newton per meter, that is what is given here, that we divide into two parts in this manner. 15 Newton per meter for the maximum intensity of triangular load and 10 Newton per meter, that is uniform distribution, that is for rectangular load. So this is how we imagine the given trapezoidal load or given uniformly varying load as a combination of a rectangular load and a triangular load. And now you replace this force by a point force one by one. That is this UDL as a point force at the center of the length and triangular load at 1/3 of its length from maximum intensity end. Here is total length 6 meters and now we'll show this triangular load. So where it is 2 meters from maximum intensity end. So this is how we show triangular load. 45 Newton, 15 into 6 divided by 2. Area of triangle formula as I told you earlier. And now this rectangular load, where it is to be shown as a point force at center of this length. So length is 6 meters, so half of the length 3 meters from end A and of course 3 meters from end B, and it is 60 Newton, as if you are finding area of rectangle. So the given trapezoidal load given uniformly varying load is combination of these 2 point forces. So that's it. To solve problems on statics, you must be able to replace distributed forces by point forces, and this is how we do it. Don't forget to like the video and subscribe my channel. You can share this video with your friends. Thank you.